Bismillahirrahmanirrahim. So guys, if you've seen the 5 episodes of Simple Harmonic Oscillator, consider this one as a bonus episode. So today we are going to write the nth energy eigenfunction in position basis in terms of Hermite polynomials. I do not claim that I've come up with this derivation all on my own. Rather, it's there in Zetly if you want to look it up. However, this video may come in handy because I've done the missing steps. So let the derivation begin. Consider an operator that has two exponential forms in position operator and the position operator itself, along with a derivative with respect to x. Since it's an operator, so let's apply it on any arbitrary wave function and evaluate further. As a first step, I have just opened up the brackets and named the two terms as a and b. Term a is quite simple, so let's evaluate term b that involves the derivative with respect to x. Using product rule, I have applied the derivative on the exponential term first and then on the wave function. Now let's go back to our parent equation, which I have named equation 1, and plug in the values there. On doing some simplification, we end up at minus x naught square d by dx. So equation 2.3.32 has nth power on the bracketed term, whereas we just took 1 as its power, so ultimately we're going to land there. However, if you observe closely, then the exponential part on which that bracketed term is acting has negative power, whereas the operator we started with has a positive power. So no worries, it's not a mistake. That's done intentionally, and the reason you will find out in a jiffy. Now let's take the power of the bracketed term as 2. We're going to evaluate it by using a minus b whole square formula, but it's not going to be evaluated in a general way because we know that operators do not commute. So the product term minus 2ab can't be written as such. It's going to be minus ab and minus ba. Now once more, let's name the terms a, b, c, and d and evaluate each of them separately. Now I have done some mistakes in evaluating all of these terms, so just keep an eye out for that, though I have corrected them in the end. Now let's plug in all of these terms b, c, and d in equation number 2 and simplify. All of the terms are going to cancel out except the term that has x naught raised to power 4 in it. And the two exponential terms cancel out because they're separated by just a number and not an operator. Now let's look at our answers that we have found, and we're going to see the pattern in them and extend that pattern to the term that has the nth power of the bracketed term. Let's see how it goes. Now I want you to recall that in the nth energy eigenfunction, we had no exponential term on the left-hand side of the bracketed term, whereas we had the exponential term with negative power on the right-hand side. So we are exactly going to make that form on the left-hand side now and see that what happens subsequently on the right-hand side. Now let's apply the operator e raised to power x square by 2x naught square from the left-hand side and simplify the equation. A note to remember that whenever we have two exponential terms with operators in the power being multiplied, we cannot add the powers straight away. Rather, this is the formula that we have to use instead. Now the equation at hand is an operator, so let's apply it on the operator e raised to power minus x square by x naught square. Okay, so I've done some simplification. Can you look closely at the left-hand side of the last equation that we got? Does it seem familiar? Yes, it does, because that's exactly what we had in the nth energy eigenfunction. Now we're going to rearrange the right-hand side of that equation to look like Hermite polynomial, because that was our goal right from the start. So let's go on about it. So what I'm doing here is separating the terms that actually come in the definition of the Hermite polynomial and putting them together in the bracket. Next up, I have separated the exponential term in two parts. The one with the negative half comes outside the bracket and the other one comes in. Now let's talk about the mathematical trick that we're going to use here. Drum rolls, please. The chain rule. Now the bracketed term is the definition of the Hermite polynomial. Let's write the nth energy eigenfunction again and write it in terms of the Hermite polynomial. And we're done. Thank you and take lots of care.